So for the continuation, so we'll have the parallel resonance. So the concept here is just the same as the concept that we did for the series resonance. So the resonant condition, so the circuit is in phase with the circuit current is in phase with the voltage applied. So which means in phase, the phase angle of the voltage and the current is 0 degrees. So as we all know, so in a resonant condition, so the circuit is resistive in nature and in resonance. And also the power factor is unity. So here, we'll be considering the uh, the circuit, the circuit which has the internal resistances. So here, I'll not derive the formulas for getting the resonant frequency, but then I'll just show the formulas considering the internal resistances, internal resistances of the circuit, and also um, considering only the pure like the RLC given. So I'll just show the difference of the formula for getting the resonant frequency. So here it is stated that the parallel resonance characteristics is that the total impedance is maximum. So why is that so? So it is stated that the admittance in which its what you call is its imaginary part is equal to 0. So admittance, its imaginary part is equal to 0 in a resonant condition. So if that's so, as we all know that the admittance is just the reciprocal of the impedance. So that would mean that if the admittance decreases, in which we are considering here only the real values because of the resonant condition that would take the imaginary part equal to 0. So that would mean that the impedance is increases or is at maximum. So why is that so? So here, let's take the consideration of the graph. So as you can see, if the what do you call this? If the frequency is lesser than the resonant frequency, so that would mean that the inductive, I mean the capacitive reactance would be more equal to the I mean would be greater than the inductive reactance, and to that the this would behave in a inductive circuit. So as you can see here, so this part here would would operate in an inductive way. So also same as true here for the other side. So if we're taking consideration if the applied or the frequency is greater than uh, the resonant frequency, so so that would mean that the inductive reactance would be greater than the capacitive reactance, and that would mean that this part here, this region would act as a capacitive circuit, in which to clearly understand. So let's take the example of it. So we have omega, the frequency is equals to 0. So that would mean that the value of the capacitive reactance, the capacitive inductance would equal to 0. So this is for the low frequency. And also, if we're taking consideration if the what they call this the frequency, the omega value is equal to infinity, then the capacitive reactance would be equal to is also equal to 0. So this would mean that both of the high and low frequency are of are at or the impedance is minimum. And to that, in the resonant condition, so that would mean that the value, the impedance would be at maximum. So as you can see here, this is our maximum impedance, in which in the resonant condition, so it is equal to the um, value of the resistance, since the resistance is purely resistive. And as for the part of the current, in which here it is stated that total current is minimum, so so it satisfies the resonant condition that that in a parallel resonance, so the current is at minimum. So as you can see here, so if we move away to the uh, if we move away to the resonant frequency, so here in the middle, so it will this will act as the inductive. So same as what is labeled here in the in in the in the frequency versus impedance graph. So and one thing is that so is the total current is minimum because so as you can see the relationship between the current and the resistance is inversely proportional. So moving to the formulas part in considering the parallel resonance, so we have so formulas. So I'll just take focus here. So in this formula, so we are just considering here, like this is resistance, a resistor, the inductor, and the capacitance, which is in parallel. So this would be the resulting formula, resonant frequency formula, if we consider here just this, like the resistor or the RLC circuit. So the resistor, inductor, the capacitance. So here in this formula, as you can see, this would be the formula of what is the first figure I that I show to you. So in which we are taking the consideration of the internal resistances the uh, of the circuit. So this would be the resulting formula. And as you can see here that this is the susceptance of the inductor, the susceptance of the capacitance. So this is just the reciprocal of what we did. So like the when you say susceptance, so it is just the reciprocal of the reactance. So we'll be dealing with this. I'll just not write the formula here, but for the exam, I'll write the formula for the upcoming example. One thing here is that we have the Q factor. So in which the Q factor is just the selectivity of the circuit, as I've uh, defined or given the definition of it in the series resonance part. So in which the Q factor here in parallel resonance is taking the consideration in the current part. So in which current a Q factor is equals to the current in inductor or the capacitor over the total current. And also here, I have forgot to encode that in the current here in parallel resonance, so is equals to current is equals to the voltage times the admittance, in which you can have the volume, the expansion of the formula, so the admittance, which upon considering the internal resistances of the circuit. So RL over RL squared, so plus XL squared plus RC or RC squared plus XC squared. So upon getting this formula, so you'll just have to take the consideration of the branches. Like for example, we'll take this is a branch, first branch which is has the value of the impedance 1. So and here the impedance 2. So that's how uh, the impedance, or I mean the impedance. I have wrote here. So the impedance is obtained. So I'll not show here the derivation. So as for the examples of parallel resonance, so we'll have the first one. So in this example, I've just given a simple example of a parallel resonance. So the given states that the coil of inductance is 31.8 millihenry. So here I've just drawn the circuit, so which is 31.8 millihenry. So just assume that my drawing is perfect. So this is the inductor, and also with its resistance of 12 ohm, and is connected in parallel with a capacitor. So a capacitor here, so as you can see, I mean sorry. So here it is now, so the corrected one. So we do have the 12 inductance and resistance, which is connected parallel to the capacitor, which is across a 250 volts, then 50 hertz supply for the resonant frequency. So determine the value of the capacitance if no reactive current is taken from the supply. So here it's an important note here. So you will be determining the value of the capacitance if the condition is no reactive current is taken from the supply. So take note that this satisfies, or this is what I stated in the parallel resonance. So the no reactive current is taken from the supply. This implies simply to the resonant condition in parallel resonance. So here, take into consideration of the given, so we can substitute directly the values. So 1 over 2 pi times the square root of 1 over the inductor, which is equals to 31.8 millihenry minus the resistance, which equals to 12 squared all over the inductor, which is 31.8 millihenry. Also, I forgot to substitute the value for our what do you call this, the resonant frequency, which is like 50 hertz. So upon solving this, so we can simplify this first, or we do have the option to just shift solve it, but then I think that this would take time, but then it's yeah, so it's okay to shift solve this. So, I mean, so there is the formula here, so I forgot to put here. So we'll just say solve the value automatically in our calculator. So shift solving. So we'll have the value of the capacitance equals to. So we'll have the value of 0.1304 milli. I mean, sorry. So it's just correct. So times 10 negative 3. So why do I consider it just a simple problem for the parallel resonance? So it's because this problem I find it's unique because of what is stated, that if no reactive current is taken from the supply, so which then simply implies that this is a parallel resonance problem. So if you know how to obtain the or to know or to identify an parallel or any circuit or what is intended for you to solve, so you can simply have the formula directly. So in this case we do have only the frequency resonant frequency that we are just considering. So moving on to the second example. So for the second example of parallel resonance, so we have the given problem. So a coil having an impedance of 10 plus J5 ohms is connected in parallel with a series combination of a variable resistance R and a capacitor having a reactance of 8 ohms. So the combination is connected across a 24 volts AC source. So we're asked to determine the current drawn. So if the R is adjusted in order to bring the total power factor of the circuit to unity. So first, let's take the consideration of the circuit. So we are given with the 24 volts AC source, and then here, so we are given an impedance of 10 plus J ohms, so in which this is our the value of the RC, and this is the value of our inductor inductance. So we do have the values of 10 ohm, then J5 here, imaginary. So it is connected parallel with a series combination of the, so here the series combination of the resistance and the capacitor. So where the R is just a, so where R is, we're going to solve this. So in order for us to have a power factor of unity, so we chooses R, and the capacitor having reactance. So reactance of the I of 8 ohms. So here the inductance we have 5 ohms, the um, the resistance which is 10 ohm, and um, the variable resistance R which is connected in series with the reactance of 8 ohms. So before answering what is asked, so let us first note that at parallel resonance, so the total admittance is just equals to the uh, total conductance, and the susceptance is 0. So we'll be taking the consideration of the susceptance of the inductor, which is equals to the susceptance of the uh, capacitor. So in which the susceptance here is just equals to the capacitive, the, yes, capacitive reactance all over uh, the RL squared plus the um, XL squared. So which is equals to the, so here um, the susceptance in the capacitor, so which is equals to the XC over R, also RC squared here, plus XC squared. So, or we can just let this as an R squared. So plugging in the values, so we have the XL which is equals to 5 over 10 squared, so RL squared plus the 5 squared, which is equals to the A over the R squared plus the um, the value of XC, which is equals to 8. So 8. So here we can just use our calculators in solving. So we'll just have to shift solve this. So we'll have the value of 11.66 ohm. And to that, so if we do have the value of the resistor, so we could solve for the uh, total current total current, so that the total power factor of the circuit would be at unity. So that would mean that that is a that is the resonant condition, that the power factor of like either in series or parallel resonance is unity. So here we can have our I total. So earlier, so we have listed down the formulas, or the basic formulas for the parallel resonance, which is used for the solving. So we have the I total, which is equals to the V total times the admittance total, so in which the admittance is just reciprocal of the impedance, and which we are considering here the admittance since we are dealing with parallel circuits, so in a parallel resonance. So to that, in substituting the values, so we do have our voltage total, which is 24 volts, and our RL, the resistor across these inductive reactance, or in series with the inductive reactance, is 10 ohms. So 10 ohms over 10 squared, so 10 ohms squared plus 5 squared. I mean, this value must be, they call this, so yeah, yeah. We're just considering the the coefficient. So 5 squared plus the value of the RC or the resistor that is parallel, I mean series with the capacitor is the so what we have solved is the so 11.66 so all over 11.66 squared, so plus the value of our capacitive reactance, which is 8 ohms. So this, we can just simply input this into our calculators. So, and we'll get the total current of this given or asked problem to be 3.32 amperes. So that would be the total current in order for us to have a uh, total of unity and total of power factor of circuitry unity.